Alright, so what I'm going to be presenting today on is called the transfer matrix method. And it's basically the way that you can solve problems in graph theory using techniques of linear algebra, and it's really cool. So you start off with what's called a graph. And a graph is just a set of vertices, as they're called. A finite set, and you can number them 1 to n if you want. And then it's a finite set of vertices that have what's called edges. So like if you have two vertices, vertice 1 and 2, then you can have an edge like this. You can have, edges have directions, by the way. That's one of the requirements. It's called a digraph, as in a directed graph. There's such thing as an undirected graph where edges don't have directions. But this is a directed graph. So you can have it in one direction, you can have it in the other direction, or you can have it in both directions. And so let's just write down a graph. Let's say 4 vertices. 1, 2, 3, and 4. And then, I don't know, so this is 1, 2, 3, and 4, and then we'll throw on some edges at random. I'm just making stuff up as I go. Alright? And so, 1 connects to 2, 2 goes to 3, etc. And so as it turns out, a useful tool is something called the adjacency matrix. And the adjacency matrix is the matrix that encodes this graph. And so it's the matrix A, where A, row I, column J, is equal to, well, 1 if there is an edge from I to J, 0 else. Okay, so for example, A12 is equal to 1. A14 is equal to 0. So I'm just going to write out this matrix, just for the sake of this. Right, so let's see. So 1 does not connect to itself. Vertices are allowed to connect to themselves. It's called a loop. But in this case, it doesn't. So 1 does not connect to 1. 1 does connect to 2. Does not connect, does not connect to 3. Does not connect to 4. 2 does not connect to 1. 2 does not connect to 2. 2 connects to 3. 2 connects to 4. I'm just going to finish this off. Alright, so that's what's called the adjacency matrix. One second, I'm just going to make sure that the camera can see everything. Alright, yeah, I'm going to move you guys a little bit closer so you can see things better. Probably won't be able to see my face very much. Alright, so then the question is, so basically the big question that we're trying to answer is about things called walks. And so when we're talking about a walk, we mean just start at one vertex, go to a different vertex, traveling along the edges. So like a walk from 1 to 4 could be 1, 2, 4. But it could also be 1, 2, 3, 4, right? Because that's allowed. But you can't do 1, 4 because there's no edge between 1 and 4. And so the question is basically just how many walks are there between one vertex and another. And this is a problem that shows up everywhere, especially in combinatorics. You can transfer a lot of problems in combinatorics into a problem in graph theory and solve it using this method. So the basic notion of it is examine, so Aij is whether or not there's a one-step walk between vertex I and vertex j. And so the question is, what happens when you examine powers of your adjacency matrix, right? So let's consider A to be some adjacency matrix. And let's imagine, let's just take a look at Aij, right? And let's square it. First. So let's look at the coefficient Ij in the entry Ij in the matrix A squared. Well, if you write out the actual matrix, you do out the multiplication, just like, by the definition of matrix multiplication. Ooh, one sec. Forget that it is equal to the summation. I'm just going to write it as the summation over k. K runs from 1 to n of a I k times a k j, right? That's just the definition of matrix multiplication. All right, but I'm going to continue this pattern. So we're going to look at what comes next. Let's look at a cubed. All right, so a cubed ij equals summation over k. I'm going to label it k1 this time because we're going to have another summation in there of, ready, a squared I comma k1 times a k1 comma j. Right? That's just matrix multiplication formula, right? And then we know this guy because it's just the previous one. So this is equal to the summation over k1 of the summation over k2 is what we'll label it. A I k2 times a k2 comma j, comma k1, all times a k1 comma j, right? And then we can actually, since multiplication is distributive, we can just write this. We don't need the parentheses there. We can just write it like that, right? And we get that. And so we can see that more generally, following this pattern, we're going to have that a to the n, the ij entry in a to the n, ij equals the sum where k1, k2 up until kn minus 1, right? There's 2 indices in this sum, there's 1 index in this sum, right? And so there's going to be n minus 1 indexes in this sum. It's going to be an n minus 1 iterated summation, right? And then the general term is going to be a I comma k1 times a k1 comma k2 times a k2 comma k3 up until, at the end you get a k n minus 2 comma k n minus 1 times a k n minus 1 comma j, right? That's going to be the general term in the nth power of aij. That has nothing to do with graph theory. This is just a fact about matrices. But what gets interesting is, get you even closer so you can see this better. What gets interesting is when you examine this actual summand, and you think of what it means in terms of matrices, right? Well, what this is this is asking you, hey, is there an edge from vertex I to vertex k1? And then is there an edge from vertex k1 to k2? Then k2 to k3, up until kn minus 2, kn minus 1, up until kn minus 1, comma j. And note that they're either 1 or 0. So if even one of those edges doesn't exist, it's 0. But if all of those edges exist, then it's 1. In particular, when all of those edges exist is when there is a walk, I to k1 to k2 up until to kn minus 1 to kj, right? This summand is exactly 1 if this walk exists, right? And this is a walk of length n. The walk is the number of arrows. So there's n plus 1 terms here, and there's n arrows. So each summand, of course, adds a 1 to the big summation whenever this walk exists, right? So this summand over all possible walks gives you the number of walks from I to j of length n, right? So that's kind of the general proposition. I'll leave this here for a second so you can see it if you didn't get the chance to examine it before. And so, yeah, so now I'm just going to write down that proposition in the more general form of the nth entry, or the ij entry of a to the n equals number of walks from I to j of length n. Right? So that's a very important fact. And so suddenly we can, for problems in graph theory, we can just create a matrix and use linear algebra to figure stuff out about that matrix. So, right, so now from this, we consider next the, because this is under the study of rational generating functions, we consider the generating function, where you fix I and j, and you fix your graph, and you consider the generating function of the number of, walks of length n, right? If we remember, a sequence fn corresponds to a generating function of x equals the sum n greater than or equal to 0 of fn x to the n, right? So in this case, the sequence that in consideration is the number of walks from I to j of length n, right? So we're going to label that f sub ij, and the parameter that they use is lambda. So we're going to use lambda, right? F sub ij of lambda is the generating function for the number of walks from I to j of length n. In other words, it's equal to the sum of n greater than or equal to 0 of the ij element of an times lambda to the n, right? And so from there, well, by linearity of matrices, you can write this as the ij element or the sum of n greater than or equal to 0 of the ij element of lambda a to the n, right? The ij element of that matrix properties, right? And then this, even more generally, when you imagine infinite series of matrices, which can be defined rigorously, this is equal to, well, it's the, so lambda a to the n, it's the ij element in the matrix, the matrix series, this guy. Sorry if this is low quality film. The ij element of this. But this, as a matter of fact, is an infinite series of matrices. And it's well known that when an infinite series of matrices converges, so if B is a matrix, then this guy right here, which is the rule that that exists from regular infinite series, regular algebra, the sum n greater than or equal to 0 of B to the n equals this thing still holds for matrices, right? So this guy up here is equal to the ij element of 1 minus lambda a inverse, right? It's the ij element of 1 minus lambda a all inverted. And so now is when we pull back to Cramer's rule, which is the rule we were talking about last time, where it says that if A is a matrix, right, then A inverse, the ij element of A inverse is equal to -1 to the I plus j times the determinant of A, where you remove row j column I. This is the notation that the book uses. You remove row j column I, all divided by the determinant of A, right? And so I'm just going to apply that up here to say that f ij of lambda equals, well, it's the ij element in this inverse. So it's equal to -1 to the I plus j times the determinant of 1 minus lambda a, where you remove column j, row I, all divided by the determinant of 1 minus lambda a. Now, let's just recall what this is equal to. This is the generating function for the sequence of the number of walks from length n from I to j. And so this guy right here, what's important to notice is that the determinant function, if you imagine writing this all out and expanding it, is that it just becomes a polynomial in lambda, right? This is a function of lambda, so this becomes a polynomial in lambda. And then you have a ratio of 2 polynomials in lambda, which means that this generating function is, in fact, a rational. It's a ratio of 2 polynomials, so it's a rational generating function. Rational generating function. In particular, its denominator is this polynomial. And so if you remember back to everything that we did last week about rational generating functions, where the denominator, the polynomial in the denominator, gave rise to, via its roots, an expression of the sequence in terms of sums of exponentials and polynomials, but also the coefficients of the polynomial gave rise to the fact that the sequence had to satisfy a linear homogeneous recurrence relation. So even just without even calculating it, we now know that the number of walks from I to j of length n has to satisfy a linear recurrence relation, and it has to be expressible in the form of some polynomials and exponentials. Now there's actually even for the specific case of a closed walk is a walk from one vertice back onto itself. So like in this diagram up here, we have 1, 2, 3 is a closed walk. We have 4, 3, 4. Oh, sorry, 1, 2, 3, 1 is a closed walk. We have 4, 3, 4 is a closed walk, etc. And so the number of closed walks from 1 to 1 is just a 1, 1. The number of closed walks of length n from 1 to 1 is just a to the n 1, 1. Same thing, a to the n 2, 2. So, and more generally, the number of closed walks of length n on the entire graph is just the trace of a to the n. Right? It's the sum of all of the diagonal elements. It's a to the n 1, 1 plus a to the n 2, 2, on and on. Right? And so that gives us this value. And this value is easy to calculate when you know the eigenvalues of the matrix. So the eigenvalues of the matrix actually, more linear algebra coming into play that allows us to solve these problems. So if you recall the trace of a matrix, by the way, let's let eigenvalues of A be lambda 1, lambda 2, lambda q. All right, those are the non-zero eigenvalues of A. Right, the trace of A is just the sum of the eigenvalues. I don't know how to prove that offhand, but we did it in our linear algebra course. It's not that difficult. And more generally, if we consider, lambda as an eigenvalue of A, right, that means that, there's a vector v such that AV equals, there's a vector v such that AV equals lambda v, right? Then upon applying A again, we get that A squared v equals lambda AV equals lambda squared v, right? So lambda squared is an eigenvalue of A squared. And in particular, that means that and more generally, lambda to the n is an eigenvalue of A to the n. So in particular, when we want to take the trace of the matrix, we can just say that the trace of A to the n is the sum of all the eigenvalues of A to the n, and the eigenvalues of A to the n are just the nth powers of the eigenvalue of A, right? So lambda 2 to the n plus on and on plus lambda q to the n. So this equals this, right? So the number of closed walks on a graph you can find for any length n just by finding the eigenvalues of the original matrix. And so yeah, so using just techniques in say linear algebra, you can solve problems of graph theory. I'm already at 20 minutes, but I wanted to give an example. I'll like very briefly go over the example that, one of the really cool examples that the book gives. So it asks for the number of, let's let P be a fixed number and denote the set P, I don't know why I drew it like that, P equals the set 1 to P. Alright, so the question is, how many sequences of length n are there, A1, A2, AN, in, as a subset of P to the n, right? So each element right here is up to 1, is 1 up to P, and such that for all I, AI is not equal to AI plus 1, and in addition, AN is not equal to A1. And so this, at first, doesn't look like a graph theory problem, but you can actually really easily turn it into one. When you imagine it as each sequence being a walk of length n, right? Or consider the graph with p vertices, p vertices, p vertices 1, 2, p, right? That's their names. And the sequence A1, A2, AN, imagine it corresponding to the walk on the graph. A1 goes to A2, goes to A3, goes to on and on up to AN, right? And an interesting trick that the book does is just, rewrite A1 at the end of it. So consider this sequence corresponding to this walk. I don't know if the camera can see that well, but consider this sequence corresponding to this walk. And if you notice, this is a closed walk of length n, right? And so the number of sequences of this is, this is a closed walk of length n on a certain graph. On the graph where every vertex is connected to every other vertex except itself, right? This little AN is not equal to A1, it corresponds to the fact that AN ties back to A1 on the loop, right? So imagine, if there's 4, right? Every vertex goes out to every other vertex. I'm not going to draw it out. But it doesn't go back to itself, right? Because that would correspond to having a walk like A1, A1 again, right? But that's but you're not allowed to do that because we made the rule that for all AI is not equal to AI plus 1. So the graph that we have left is, so now we consider the adjacency matrix of that graph, and the idea is that you have Aij equals, well, if they're two different elements, then it's one. They can be connected, right? If I not equal to j, but if they're equal, then you're not allowed to do that. So this is if I equal j. So in particular, if we imagine this matrix, then we have the fact that it's the all ones matrix, except it's missing the middle diagonal. So if we add the identity matrix, AI, this is equal to what we'll call J, is all ones matrix, right? And so from here, what we can do is we can try and find the eigenvalues of A using this fact. So for starters, the matrix J, it's all ones, meaning that every single row is linearly dependent on the first row. Sorry, every single column is linearly dependent on the first column just because it's equal to the first column. So the amount of times that 0 appears as an eigenvalue on J is p minus 1 times. Like if you imagine, for example, this can be explicitly done. I don't know. Let's take like the 3x3 case. The question is, well, it's got rank 1. Sorry. So that means that the dimension of its null space is exactly 2. Dimension of the null space exactly 2 means there's 2 linearly independent vectors that give us 0 eigenvalue. In this case, it's actually just not hard to find at all. Like 1, -1, 0, but also 0, 1, -1. These are linearly independent and they give 0 eigenvectors. They give eigenvectors of 0. And so, from there we can conclude that the element 0 occurs as an eigenvector on J, p minus 1 times. Sorry, I think I might have said A before, but I mean P, because it's a P by P matrix. A is P by P. And so whenever 0 is an eigenvalue of J, right, we have A plus I acting on V equals 0, then that's corresponding to a V equals -1 times V, right? Times I, but that's kind of a given, right? So that means that -1 occurs as an eigenvalue for A exactly P minus 1 times. It's the amount of times that 0 occurs as an eigenvalue for J. So lambda 1, lambda 2, up into lambda P minus 1 equals -1. Alternatively, you can also note that, and so there's P eigenvalues, right? And so the question is, what's the Pth eigenvalue? And if you note that the sum of the eigenvalues always equals the trace of the matrix, right? So lambda 1 plus on and on plus lambda, P minus 1 plus lambda P equals the trace of the matrix. Well, this matrix is 0 on its diagonal, right? So it's 0. And this together, there's P minus 1 negative ones, right? So this is negative P minus 1. So you conclude that lambda P equals P minus 1, right? So those are your P eigenvalues. And then if we remember that the number of closed walks of length n on a graph is just the sum of the eigenvalues raised to the n. So in particular, the solution to this problem, number of such sequences, is just it's lambda 1 to the n sequences, I should say, of length n that we defined above, is lambda 1 to the n plus lambda 2 to the n plus lambda P to the n. Well, there's P minus 1 copies of -1 corresponding to up here, and there's 1 copy of P minus 1. So this is equal to P minus 1 to the n plus, corresponding to this eigenvalue, plus P minus 1 times -1 to the n, corresponding to the P minus 1 copies of this eigenvalue. So that's how you can use linear algebra to solve that question originally. So, the number of sequences of length 4 where no two consecutive terms are the same and the first is not equal to the last is equal to 4 minus 1 to the n plus 4 minus 1 times -1 to the n, right? It's this sequence right here for a fixed P, right? Where in that case I fixed P is 4. Alright, well, let me know if you have any questions. Hope you understood everything.